Why does it keep cutting my head off? I am not sure. All right, good morning, geometry class, or good afternoon, good evening, whatever it may be for you, who knows, whatever time you're coming on and looking at this classroom. All right, we're on 10.7. Okay, this is Tuesday, so we're looking at tessellations. Okay, now what is a tessellation? Actually, you've seen tessellations everywhere. Actually, I'd like for you, we can count this as a homework assignment. Okay, take pictures of 5 tessellations. Now you probably don't know what it is yet. We'll explain that later, but 5 pictures of tessellations that you see around, just around house or anywhere you go, but 5 of those will count as a homework assignment. All right, I'm going to try to adjust this so that you can see all of me. All right, I don't know why that is, but it just keeps cutting me off. Okay, we're just going to have to go back a little bit. Hopefully I don't wreck and break everything. Okay, tessellation. So now, what is a tessellation? Okay, this is actually an example of triangles. Now you see the same triangle repeated over and over again. Okay, this would be what's called a regular tessellation. All these triangles are the same size. Now, because they're the same size, and this won't work for every shape. Okay, but if you take those triangles and you push them all together, okay, there will be no gaps in between. Okay, and you've seen tile floors are done this way. You don't usually see triangle tile floors, but you see rectangles or square tiles because a square fits good. Now, not every shape does this, as we'll see. I heard of a guy, one of my students once said, try to do this with pentagons. And I wish he would have checked out the math before, because if you check it out, a pentagon, a regular pentagon, where all of them are the same size and same angles, they won't fit together. And so this guy made these pentagons, and he cut them all out and was going to tile something, either a pathway outside or something, and then he found out he had all these gaps, so he had to put little pieces of different things inside of them. Would have helped to know that pentagons don't tessellate, but he didn't know the math. All right, so anyways, in design you see these a lot. Triangles tessellate, hexagons tessellate. Actually, the way you can see this, or you think about a beehive. They're little hexagons and they all fit perfectly. It's amazing that God put that in a bee's mind to be able to do that, for that to work the best. Okay, if they were any other shape, they wouldn't be able to do what they do. So it's amazing how in God's creation, God has mathematically enabled the bee to figure that out. Okay, it's not the bee that's smart, although some may argue that. It's the God that's created the bee. All right, so let's move on. Okay, a tessellation, here's the definition, of a planar region is a coverage of the region with one or more figures so that there are no overlaps or gaps. Okay, I drew here rectangular gaps. Looking at this, how does the brightness look here for you? All right, get it brighter. Whew. All right, I think that's as low as we can get it. All right, I can tell that white's a little bright, but hopefully you can see that okay. Let me know. Feel free to comment in there if you can't see it accurately with that. All right, so that's what a tessellation. Okay, like we said, squares, rectangles tessellate, triangles tessellate, hexagons tessellate, but there are some shapes that don't tessellate, so we're going to look at those. Okay, a regular tessellation uses a single regular polygon to tile the region. Okay, to avoid gaps or overlaps, the angle measure at each vertex of the regular polygon must be a factor of 360. So what we're going to do is we're going to find the individual interior angles and see if that angle is divisible by 360. If it is, it will tessellate. If it isn't, it won't tessellate. So we're going to work that out. All right, so now what we have to remember is, how do I calculate the interior angle of polygon? All right, and this is that formula there, n minus 2 times 180 divided by n, where n is the number of sides of the polygon. Okay, maybe I'm going too fast for you. Remember, you can always pause this video, go back to it, listen to what I said. N, again, is the number of sides in the polygon. Okay, if we remember this from the shapes, okay, I'll draw a shape here. If we drew let's draw here a hexagon. Well, how many triangles will fit inside of that hexagon without overlapping? 1, 2, 3, 4. Okay, remember, there's always 2 less. We have 6 sides, 2 less triangle will fit in there. 4. And how many degrees does each triangle have in it? 180. So we multiply that by 180. but then we want each individually, so I have to divide it by the total number of sides. So we would do that, okay? All right, so let's do that, I'm sorry. Before we reveal this, we're gonna look at that. So n minus 2, now let's see for this. Determine whether each regular polygon can be used to create. All right, talking about the triangle. Well, how many sides does it have? Well, it has 3. So 3 minus 2, which is 1. Multiply it by 180, which we already know. Yes, okay, a triangle has 1 times 180. It has 180 degrees total. The sum of any 3 angles of a triangle is 180. Now, all right, what we just want to know, one of them. So we divide by the number of vertices, which would be 3, the number of angles. Okay, divide that by 3, it's 60. All right, so each one would be 60, which we knew that, and we could calculate that without putting it into the formula. You know, 180, if it's regular, that means each one of them is the same, which would be 60 degrees. Now, 360, 60. 360 divided by 60, does that go in evenly? Yes, it does. Okay, and we'll see that right here. Okay, click on that. All right, okay, each angle in a regular triangle measures 60 degrees. 6 degrees is a factor of 360. Okay, meaning it's divisible. So yes, a triangle can be used. It can tessellate. We can take a triangle and piece them together to make a tessellation. Like we said, we can do this in design. All right, determine whether each regular polygon can be used to create a regular tessellation. Now an octagon. Will an octagon tessellate? Okay, we're going to use that formula. What was the formula? Can you remember it? You got it? Oh, I see that hand. What's the answer there, Stephen? Just kidding. I know y'all aren't here. Maybe he's raising his hand, maybe he's not. All right, so what is the answer there? Maybe it's Steven's answering me here. But you've got 8 sides, so if we subtract 8, subtract 2, so that means 6 triangles would fit inside of an octagon. We multiply that by 180, divide it by, an octagon has 8 sides, divide that by 8. All right, now I don't know what that actual calculation is, but we will, okay, we'll move that box. All right, so when you take each angle in a regular octagon measures 135. 135 is not a factor of 360. If you take 360 and you divide it by 135, it doesn't go in evenly. So an octagon will not tessellate. I can't take one octagon after another and piece them together. There will be empty spaces. Okay, and you can maybe visually figure that out. But this shows me beforehand, I don't have to do it. I know based on the formula that it will not do that. All right, now we're going to label our tessellations by certain numbers. Okay, and this is how we're going to do this. Okay, what you're going to do is you're going to go to the vertice where all of my triangles are to one vertice here, or one point. Do you see that point there? Okay, we go to one point. Now we're going to look at all of the surrounding shapes. Now they're not always going to be regular tessellations, okay? They're going to be, some of them are going to have different sides, okay? They're going to be different shapes, and they're going to piece these together. So we look at this, we'll number them each by how many sides they have. Well, they're all triangles here. 3, 3, 3, 3, 3, 3. All right? Okay, so when we label this, and I believe it is that you start with the lowest number and then go from there. All right? Well, in this case, they're all the same. So we have 6 3s. So I would label this tessellation as a 3, 3, 3, 3, 3, 3. All right? Just go to the point and count. Okay? Going there either left or right doesn't matter, but start with the smallest one. All right, now we have different types of tessellations. We've just looked at regular ones. Now let's look at different ones. Okay, a semi-regular tessellations are made from 2 or more regular polygon figures with the same arrangement of polygons at each vertex. Okay, are made from 2 or more regular polygon figures with the same arrangements of polygons at each. So what we have here, semi-regular, they're not all the same shape, but they are both, all of them are regular. Now, we go here and we want to label this one. All right, so we go, look at this. Okay, we'll take some vertice here. All right, so let's go right here at some point where it intersects. Okay, now, what we're going to do is we're going to go around their count. All right, we've got 1, 2, 3, 4, 5, 6, 7, 8. You've got an octagon here, okay, that hits it. All right, we'll go to the next shape. I'm going to go this way, or I could go this way, doesn't matter. This shape has 4 in it. This one has 8. Okay, and that's actually it. All right, we see that those shapes touch this point. All right, started with the 8 and I went around there, 4, 8. Now, like I said before, okay, we're going to go ahead and start with the smallest. So this would be, we could label this, this would be a 4, 8, 8. All right, and we'll see that. Okay, let's go ahead and reveal this. All right, yeah, okay, a 4, 8, 8 tessellation. Okay, a polygon with the least number of vertices is typically listed first, okay, with the least. All right, we said that earlier. I didn't know if I had it on the PowerPoint or not. Okay, but a polygon with the least number of vertices, we list that first. So we look at there, and that would be 4. Okay, that's 4 vertices with 4 sides. Okay, tessellations that are neither regular nor semi-regular are called irregular. All right, so irregular shapes are going to be ones that have different lengths. Okay, translations, reflections, and rotations are often used to create these tessellations on computer programs and things like that. Okay, you can translate them, slide them, okay, make copies of them, and slide them and make all these. Maybe some of you have done that where you copy and paste figures, you slide them and paste them into them, or maybe you reflect them to make a different type of unique design. Use a reflection, reflect it over itself. All right, example number 3. Okay, use a parallelogram ABCD to create a tessellation by performing transformations in the plane. All right, so they give us this figure right here, this parallelogram. All right, what would we do here? Okay, here we have a translation where you could slide the figure and put it right beside each other, and then put that one right beside her. Now, what I could do is I could shift it down and continue it to make it look just the same way, and it all would be going this way. What they chose to do, and we'll see as this book, is that they reflected it then. Okay, you could use reflections. Okay, we'll look here. After we use the translations, we could reflect it. Okay, reflect it, okay, and then reflect that over top of that and keep using a reflection. Okay, and we see here we have a tessellation. We've got no gaps, and these pieces fit and create this design. Okay, now that's it. Pretty short lesson. Your homework assignment will be 1 through 30. Like I said, we'll have some Zoom sessions where you can ask me questions live, where we'll go over the homework, we'll go over the test review. Hopefully this is clearly explained to you. Again, if it's not, go on. Probably the best place to go is go on Google Classroom, write a little note. If you need some extra help or whatever, and I have the time availability to do it, we'll help you as best as we can. Hopefully you're having a great day, and we'll talk to you later. Bye.